Good morning, everyone. This is the second lecture of our Stats 205. And in the last lecture, we went over the syllabus and we just began the discussion about the simple linear model. And today we're going to continue to talk about multiple linear model or multivariate linear model. Before that, I want to make an announcement about the office hour Zoom link. So it's a different Zoom link and you can find it in the CCLE homepage. That's the first thing. And the second thing is that I plan to assign the first homework in week 2. So you should also access it on CCLE, and I'll make an announcement when I assign it. So now let's continue our discussion. And the third thing is that, so please make sure you check CCLE for the updated lecture notes after lecture, because when I prepare for each lecture, I will spot some inaccuracies in the previous notes because they were subscribed by previous students. So I will correct those inaccuracies and repost the notes. So please make sure that you check back later. All right, so we stop at the MLE, M hat, last time, right? So we said that probably I should reintroduce the notation. So here, maybe I'll just clarify it again. So here we use some vector notations to make our formula simpler. Here the vector y is what we call the response variable vector. It is random with an n-dimensional, so that's y. And design matrix is we'll call it n by p matrix, but please make sure that you understand that it already includes the intercept. So the first column contains n ones, and that's the intercept. And then we can write the remaining as, let me call it x1, 1 to x, sorry, I should use lowercase, x11 to x1 p minus 1. So since this is p dimensional, except the intercept, we'll include p minus 1 predictors. And the last one, xn1 to xn p minus 1. What does it mean? It means that x11 means the first observation of the first predictor. And xn1 means the nth observation of the first predictor. So the first index stands for the observation. The second index stands for the feature or predictor. And we can also write this as a stack of row vectors. So in that case, we wrote as x1 transpose to xn transpose, where xi transpose is the covariate vector, some people call it covariate vector of the ith observation. Okay, and the next one is beta. So beta is our coefficient vector. So to be consistent with our previous notations, we will write it as beta 0, beta 1 to beta p minus 1. So you can see it's a p-dimensional vector. And beta 0 corresponds to intercept. Beta 1, the slope of feature 1. Beta p minus 1, the slope of feature p minus 1. So we're going to do matrix multiplication. And 1, so that means we can write y equals x times beta plus epsilon. And of course, epsilon has the same dimension as y. So it's n-dimensional epsilon 1 to epsilon m. And they are the error terms. So last time we gave you a very brief discussion about fixed design and random design. And I already posted that notes on CCLE, so you can check out for the technical details. But just in short, you can see that the key different assumption for fixed design and random design, I'm going to list it here again. So the key assumption for random design is that you will need to assume a joint distribution for each pair of response and predictors. So you need to have assume that xi transpose y. I read it this way. I should use uppercase. Xi transpose y. Yi they are IID from some joint distribution. You need this. And furthermore, you need to assume that this is independent. This pair is independent of epsilon I. And epsilon I by itself, it may come from some other distribution. So for example, we can still assume it comes from normal, zero mean, sigma square variance. So this is what you assume for the random design. The key is the IID of Xi transpose Yi. While under the fixed design, you assume your X1 transpose to Xn transpose are fixed. And the only random variables are the epsilon i's that are IID from normal distribution. And also, this assumption can be relaxed, okay? Just make sure that this is like the classic assumption, but this can be relaxed. So you may just assume IID, but do not specify the error term to be Gaussian. And we'll give you a little bit discussion about that when we talk about the distribution of the OLS estimate. So you see that by the definition of random design and fixed design, theoretically, they are quite different, right? Because when you say derive the distribution of beta hat, under the fixed design, the beta hat covariance matrix can just include those lowercase x1 to xn because they're fixed. But if you're under random design, then that covariance term will involve something related to the expectation of xi, not just xi, because xi is considered to be random. So theoretically, they will be different. And as a result, in econometrics, because they assume random design more often, the plugin estimator for the covariance matrix of beta hat, maybe I should say it. Last time we said MLD under the Gaussian assumption. So I put it here. Under the Gaussian assumption and fixed design. That's what we did last time. Give us this. Beta hat is X transpose X inverse X transpose Y. That's what we derived last time. And we said that this is what we call the ordinary least square estimator. And it's a coincidence that they just agree with each other. The OLS can be derived just by solving the squared loss function by minimizing that loss and using the matrix derivative, you can get it. But surprisingly, that loss function, minimizing that loss function is equivalent to MLD. So that's what we did last time, and it's right here. So maximize the log likelihood turns out to be equivalent to minimizing the square loss. So then the next question is, what's its variance, right? Last time we derived, we said that its expectation is just beta, of course, under the fixed design. And its variance under the fixed design, it will be sigma squared, that's the variance of the error term, times X transpose X inverse. So as you can see, this is a P by P covariance matrix. And this is under the fixed design. But under the random design, which I'm not going to talk about here, so the variance will not be of this form. Because in the random design, this term will be random. So you cannot just put it here. You cannot include the random term in the covariance matrix. So you need to take some expectation. So I think that's something you can check out. And because of that, and it will involve some expectation. So in econometrics, people use plugin to estimate this variance. And that will give us a so-called sandwich estimator. That's in the notes. But in our case, you see, in the variance, the only term that's unknown to us is the sigma square, right? We just need to estimate that. And how do we estimate sigma square? We can still do MLD. So this is still unknown. So we need sigma square hat to do plugin estimation. And plugin is the most commonly used approach for estimation statistics. That is, if your estimator itself involves, or if the quantity you're interested in involves some unknown parameter, then plugin means that you replace that parameter by an estimator of that parameter, and that's it. So to do that, we need to come back to our log likelihood. Okay, so it's right here. And this is what we have in the log likelihood last time, right? We have sigma square in the first term and sigma square right here. And our goal is to find the sigma square to maximize this whole thing. Okay, and it's not easy to show that, since here we have two things to find as maximizer. One is beta, one is sigma square. We need to find them to jointly maximize the log likelihood. But it's not difficult to show that here the sigma square MLE is just, I'll call this sigma square MLE, it's just 1 over n summation I from 1 to n yi minus xi transpose beta hat square. And the beta hat is what we have from the Euler X or MLE. So we can easily show this will be the solution. And this is what? So in linear regression, we actually give this term a name. And this term is often denoted as EI. And it's called the residual. Please make sure that here we distinct EI from epsilon I. So that's often assumed or written to be the same, or just loosely, I would say in a sloppy way, just written, use the same notation, but that's not correct because their meanings are different. So the residual EI, it depends on our estimated parameter beta hat. It depends on beta hat. And it is something we can observe, right? We fit a model to our data, and then we obtain the residuals. In contrast, the epsilon i's are not observable. They are just part of our model, and they are assumed random quantities. You will never observe it unless you know the true beta, but you don't. So epsilon i's are concepts that are not observable, while EI's are observable. So that's the key difference. And so now, given this, right, of course we can do the plugin, but one thing we need to deal with is to check whether this is a good estimator. Okay, so again, we're going to check the variance and the bias, or we're going to check whether it's biased, because for plugin estimator, it's very important that it's an unbiased estimator. And so that can make sure that, okay, we know, even though it's random, that means if we get a different sample, xi, yi's, so set of xi, yi's, this value will change. But being unbiased means that we know if I obtain multiple realizations of this random variable, its distribution will be centered at its true value. So that will give me some confidence in using it for plugin. But if it's biased, then its center is not the true value. Okay, so then to help us with this, we're still going to write it as a vector form. So now let's define the vector E as the residual vector, E1 to En, n-dimensional. So then clearly we can write this as 1 over n E transpose E. That's the vector representation. And then what's E? So think about the vector form. We know E is actually equal to y minus x beta hat, okay? And now we're going to use the formula for beta hat, and let's see. So essentially, let's put it here, E equals y minus x beta hat, and we know that beta hat is equal to x transpose x inverse x transpose y. So now this becomes the key, right? It's the linear transformation on y. So the first term is about y, second term is also about y. Basically, E is just a function of y. And to simplify that, we give this matrix, which has a quite symmetric form, we call it H. And this is what we call hat matrix. Okay, with this notation H, we can easily write this as an identity matrix with n dimensions minus H matrix, hat matrix, times y. That's our residual vector. And just as a side note, the hat matrix has some very interesting and nice properties, and we're going to revisit it very soon in our next 2 lectures. So the first one is that the hat matrix, clearly you can see, I'll write here, properties of H. The first one is that the hat matrix is symmetric. Symmetric, which means its transpose is itself. The second one is that the hat matrix is called idempotent. This is a term in linear algebra. It means that the square of a matrix is equal to itself. So when you take square, it remains the same. And the third thing is regarding its trace. So because of its special form, we can use the cycling property of trace, and we can see that it has a very interesting result. So because of the cycling property, we can move X transpose to the front. So it will be equal to X transpose X times X transpose X inverse. Right, now we have cancellation. And because this matrix X transpose X is p-dimensional, so p-dimensional matrix times its inverse, we get an identity matrix with p dimensions. And so clearly the trace is just p. Okay, and so then clearly you can have the trace of I minus H as M minus P, I M minus H. That's here. And so the symmetric property and idempotent property also applies to I minus H. I'll put it here. So I minus H, obviously this is still symmetric, and IN minus H squared is still IN minus H. Okay, so these are the properties we have for the residual vector, and it will be very useful for our calculation of the bias for the MLE. So now let's actually look at this estimator. Okay, so one thing we can show for the estimator for this thing, okay, I should put it down a little bit, this thing, right? So we can also write it in this way. So 1 over n summation I from 1 to n EI squared. So probably for some of you, this is easier to see. And then from here, you can go to the vector form. But what's the distribution of that? That's the key thing. So one thing we can actually say is that if we multiply it by n, so n times sigma square hat MLE, okay? So this is what? This is just the summation of EI squares, this residuals. But what's its distribution? It follows what distribution? So one thing we actually know about the sum of independent normal, sum of the independent squared standard normal variables is the chi-square distribution. So one thing we can know is that, let me just use the epsilon i's as example. So we have epsilon 1 to epsilon n. They are IID normal, but they're not standard normal because the variance is not 1. So what can we do? We can divide the sigma to the left-hand side, pretending it's known. So we have epsilon 1 over sigma to epsilon n over sigma. These are IID standard normal. And then by the definition of chi-square distribution, we can have the sum of the squares of those, that is sigma squared in the denominator, I from 1 to n epsilon I squared. This will follow chi-square distribution with n degrees of freedom. That's what we have as the definition of chi-square distribution. How about here? So one thing I want to say is that this one is the first thing to note is that E1 to En are not independent. This is the first thing we want to keep in mind. So this can also demonstrate why this is different from these, because the epsilon 1 to epsilon are independent error terms, but the residuals are not. This can be clearly seen from this formula. E is in this In minus H times Y, right? So although Y1 to Yn in this Y vector, they are independent, but this matrix on the left-hand side is not diagonal. So that's why every residual EI will involve multiple YI, making them not independent of each other. This is the first thing to know. And then how can we derive this? To do this, we will actually need to still utilize this fact, and also we're going to utilize the trace over here. So I'm not going to give you the detail about the derivation, but if you're interested, you can check it online. And I'm also going to post a very good note I found from UC Davis about the asymptotics of the regression estimators to RCCLE. So it contains a lot of detail you can check. But the result is that we can show, and this one, summation I from 1 to n EI squared over sigma squared. We can show that this follows chi-square with n minus p degrees of freedom. And here the n minus p is actually the trace, equal to the trace of this I minus h over here. So basically, roughly or intuitively, you can think of the trace of this matrix that left multiplies y as its degrees of freedom. So if it's just an identity matrix, clearly its trace is n, right? And then the degrees of freedom here is n, because y1 to yn, those n random variables, each of them can vary freely. That's the definition of independence. That means, okay, I changed my y1, has nothing to do with y2, has nothing to do with yn. That's n degrees of freedom. But now they are constrained by this thing, which means that in the E, the y, so how yi's change, so for example, the change of y1 will not directly affect E1, but E1 will also depend on other yi's. So that constraint actually reduces the degrees of freedom of E. And let me think of another example to explain to you. So if I have the average, okay, so if I have the average of y1 to yn, I call that y bar. So that's just like, that is equivalent, I just do a row vector of ones, or of 1 over n, that row vector multiplied by y. That will give me the average. In that case, what will be the degrees of freedom of y bar? That's just 1. Because y bar is just one value, and in that case, you can, that's a bad example. I should say it's a matrix, it's a matrix of 1 over n. It's a square matrix 1 over n. So I do this left multiplication for y, and then I will get a vector with y bar to y bar. Okay, what's the degrees of freedom of that? That's just 1. If you think about that matrix, the trace is 1 over n sum time plus 1 over n plus 1 over n for n times. That trace is 1. So why is that just 1 degrees of freedom? Because in this vector, all the n elements are just y bar. So if you change one of them, the rest n minus 1 will be changed accordingly. So that's what we mean 1 degree of freedom. You only can change one thing. And here we say that you have we have n minus p degrees of freedom, which means that you could have n minus p things that change differently. And after you change those, the remaining P items in E will be fixed. That's what I mean by n minus P degrees of freedom. So you don't have n things to change. You just have n minus P things to change. Okay, so coming back to this result, this gives us a way to estimate the bias because we know what's the expectation of a chi-square distribution. All right, so basically this is equal to n times sigma square hat MLE over sigma square. Okay, and this using the property that for chi-square distribution, chi-square random variable, the expectation is equal to the degree of freedom. So therefore, we know the expectation of n times this MLE is n minus P. Okay, so clearly we would have its expectation not biased, but n minus P over n times sigma squared. So it's a biased estimator. Then how do we correct the bias? The very obvious way is to multiply n over n minus P to this side, and we're done. So that bias correction is very similar to the sample variance you are familiar with, or the one you learned from the undergraduate class or R100B here. So here we propose an unbiased estimator. So we're going to call this as the sigma square hat. Unbiased estimator would be just n times sigma square hat MLE divided by n minus P. And if we write it as residuals, it's just 1 over n minus P, now 1 over m, the summation of residuals. That's the unbiased estimator. And you can see that how many, by this denominator is essentially the degrees of freedom. So then if you rethink why do we divide n minus 1 for our sample variance, you will see because in that case, you are just losing 1 degrees of freedom by using your sample mean as the center instead of the population mean for the variance estimator. Okay, so this term also has a name which we will see later as in our discussion of ANOVA. So this term, we are going to have 2 names for it in this class. The first one is often called RSS. You will see this in some books. RSS stands for residual sum of squares. Or in the ANOVA table, this is going to be called SSE. And this stands for sum of squared errors. And they're just 2 different names for the same quantity. You know, it's basically you take the square of residuals and you take the sum. Okay, so after so much discussion, and with this, finally, we would be able to say, okay, for the variance of beta hat, covariance matrix of beta hat, we can do the plugging. So now we're going to use the unbiased estimator times X transpose X inverse. And since we're under fixed design, this is known, and we're done. So then what's the distribution of beta hat then? So under the, this is something I'm going to talk about. Under this normality assumption, then clearly you can see that we can say the Y, right? The Y would follow a multivariate normal, n-dimensional normal, with a mean as X beta, with the variance as what? With the variance as just sigma squared times the identity matrix. That's it. Then with this, I can see that my beta hat, then given that beta hat is just a linear transformation of y, x transpose x inverse x transpose y, right? This part is fixed, so it's the fixed transformation of y. Then what I can do is that I basically can multiply this into this and do the transformation. So you can see that obviously I'm going to skip the derivation because I already done that. This will follow normal distribution, but mean beta and the covariance matrix sigma square x transpose x inverse. So here, under this normality assumption, our beta hat, the Unbiased Estimator will be exactly following multivariate normal distribution. So this is a p-dimensional normal, this is an n-dimensional normal. I can mark it here. But what if we are not under this assumption? Okay, if we just have epsilon IID, but we don't know whether it's normal or not, still, we can use asymptotics to derive an asymptotic normality for beta hat. So in that case, we are going to need something like, so for in that case, we're going to say, okay, the beta hat, there is some convergence. So basically, we're going to say, okay, root n times beta hat minus beta, this is going to converge in distribution to some normal zero mean and some covariance over there. So I'm not going to write it down exactly because it will involve something like you would get n out of here. And so in this term, there will not be n. So you will see there will be n because, for example, if you think about the first column in X, that's all ones, right? So that will become the first row in X transpose. You have ones. So here's a row of ones. Here's a column of ones. So their multiplication will give you an n. And you have actually a term related to n in every term in this P by P matrix. And if you take the inverse, that n will come out as 1 over n. And that 1 over n multiplied to this left-hand side will give you a root n. So you can think of it that way. But after doing that, so this term will be standardized. So you will not include n, the sample size, in this. So I'm not going to write it down. But basically, you can still do this. And even under random design. So even under random design, you can still have the asymptotic normality. But the thing is that if you're under random design, when you will need to have some, you will need to use the Slutsky theorem because you have a ratio. Like one term is about the beta hat and the other term is about the x. You are going to have x over there. So that will have, you will need to say, okay, this term is converging in its expectation by the law of large numbers. You have one term converge in distribution, one term converge in probability, and the Slutsky theorem can combine the two. So basically, for this one, you're going to use the central limit theorem and maybe you may need to have the Slutsky, yeah, to prove it, asymptotic normality. But since we're dealing with a simpler case here, we're just going to say, okay, under this assumption, it will be easier for us. So we don't need to worry about those asymptotics in this class. But I think some of you have taken my previous class about the large sample theory. So then you should know what I was saying. Yeah, so we can actually derive this, even without normality assumption. And for the rest of the class, it's okay if you skip this part. But if you're interested, you can check the note I will post. But one more thing is to read backwardly. This can actually justify why normality assumption is so widely used and why people think it's reasonable. I would say central limit theorem plays a key role. Because central limit theorem tells us, okay, if our statistic, like beta hat, can be written as some form of average of independent random variables, then we can use the central limit theorem to have an asymptotic normality. That means if my sample size is large, it will be roughly normal. And so then in backwards, it will say, okay, normal distribution is definitely the most common distribution. So as a result, assuming the normal assumption is not super ridiculous. And also, if you think about the error terms as some measurement errors, we know that in our natural world, a lot of measurement errors are normally distributed. I think that's still as a result of the central limit theorem. So that's something very good to know. Okay, so now with this, finally, we said we're interested in doing the inference, right? By inference, we mean that we are interested in each slope parameter, inference of beta j. Then we have a lot of tools at hand. Then how do we do it? So by inference of beta j, the key idea is that we want to say something about beta j given our estimator. Okay, so this means that using beta j hat to do inference of beta j. So in statistical inference, it's not sufficient. We just say, okay, beta hat j is our estimate because it's just a point estimate or it's just one value. We want to say about its uncertainty so we can know better about beta j. So one thing to do statistical inference, or the most common way to do it, is to do hypothesis testing, right? So you may want to test for this. The null hypothesis is that beta j equal to 0, and versus the alternative hypothesis that beta j is not equal to 0. Why are we interested in this question? Because in linear regression, this will reflect whether predictor j has an effect on my response or not. In social science, often people are trying to make some statement or some observations based on this test. So for example, you want to know whether the education level does have an effect on people's income level. And also in health sciences, you may want to know whether a drug does have an effect on the recovery. So those are all hypothesis testing problems. And here, to do this hypothesis test, then a very natural way to construct the test statistic is to use beta j hat. How do we do it? So here we have something called a t statistic. So in the linear regression setting, the t statistic is defined as, I'm going to use uppercase for it because it's a random variable. It's defined as beta j hat divided by the square root of its estimated variance. So we put hat on variance because it's the estimated variance, it's not a true variance. The true variance will involve sigma, which is unknown. So this is what? We write it out, and this is actually equal to beta j hat divided by sigma hat, the unbiased estimator. So there's no square, it's just sigma hat, times the jth diagonal entry of x transpose x inverse. So that will take the jth diagonal entry and then take the square root, and that will be the constant here. Okay, so you see, we're just using that for the beta j hat, we divide by its standard error. So we have a term for this, it's the standard error. And the standard error is basically, you can actually remind yourself of this concept, standard error here again. Standard error is what we call the square root of the estimated variance. So when you say standard error, you understand that it already involves some plug-in terms so that it's observable. Okay, so then why do we want to call this a t statistic? Because an interesting fact is that this follows a t distribution. Okay, so this follows a t distribution with n minus p degrees of freedom. And this is similar to the t-test we use for that mean, right? For testing whether the mean is 0. But so that's why we use the same name. But why is this following a t-distribution? And also, why does it matter? So you may wonder, why cannot I just use the beta j hat itself as the test statistic? Because I already have its distribution here, right? This is the joint distribution of beta 1 hat to beta 0 hat, beta 1 hat to beta p minus 1 hat. I have that. I can use beta j hat as my test statistic. I can still do the calculation for p-value. Then why do I want to standardize as a t-statistic? The reason is still in the old times, we don't have computers. So a lot of computation that seemed trivial or easy now was not that easy or was very difficult in old times. So that's why people have to find several standardized distributions for use. T distribution is 1, chi-square distribution is 1, and of course, normal distribution is 1. So that's why we need to standardize a lot of things. So then we can use this, the pre-calculated table. If you still remember, in many undergraduate textbooks, we have that table for T distribution, for normal distribution. So then you can, once you have a test statistic calculated based on your observed data, then you can look up what's the tail probability of the test statistic value in that table, and then you can get an approximate p-value. So that's why we're still, I think some classes are still teaching that in the undergraduate class. But nowadays, I just want to let you know that with computers, you don't necessarily have to use T as your own test statistic. You could also use beta j hat, and using its distribution, you can still get a p-value. There's nothing wrong with that. It's just in the old times with the standardized distribution, it will make computation possible. And also for your information, a lot of the statisticians are pioneers in the field 100 years ago. They spent years of efforts just trying to get the quantiles of a standard distribution, like T distribution. So they want to compute what is the, say, 95% percentile for T with this degrees of freedom. So that's a tremendous task in those times. All right, so now one more thing I want to say is that why does this ratio follows T distribution? Okay, this is something we also covered in the undergraduate 100B here. So that's why I said that class is a very important prerequisite for my class. So why is this?
Professor, so I have a question. So if say you are using the beta j itself as the test statistics, it involves the unknown like parameter of sigma square, right?
We're going to do plug-in. It's actually the same. So we're going to just plug in the sigma hat into here. So when we calculate the p-value, so that is use the normal distribution
as the. Okay.
Yeah, so that's something I want to say later. So in the T statistic, so it's basically here you don't have any unknown parameters, and it's actually a finite distribution. But we know that this distribution itself, as n goes to infinity, is convergent to normal 0, 1. So that's why if I do that, I do the plug-in, I use normal distribution. Basically, it will be equivalent that I do assume this T follows standard normal. Yeah, and also when your n is reasonably big, then using standard normal to replace T distribution doesn't hurt you too much.
Yeah,
and also if you're under this asymptotics, like if you don't have this normal assumption for epsilon I, you're just using the asymptotics, okay, right here, then you have to use normal anyway. So that's why, to me, unless your n is super small, that you have to make this error term normal assumption, I think using normal instead of T is totally fine.
Okay.
Yeah, so I think this is a very good example for you to think out of the box. A lot of times, statistics as a discipline, this whole derivation involves a lot of approximations. For example, asymptotics itself is an approximation, right? You're just doing approximation when n is large. So if you really understand the concept, a lot of times you have to challenge the existing wisdom. You want to think, okay, do I really need this? Can I get rid of this? Or can I change the procedure? Is it still well justified? So asking yourself those questions can really make yourself a statistician. So I learned from my professor in PhD that, and I think it's a very interesting saying. I think it's good to share with you guys. So the professor says, applied statistician is not statistical, applied statistician is not data analyst. So you see, what's the difference between the two things? So the first time, so I think what the professor meant was that applied statistician, you need to have some of your own insights into the methodology. And also that can give you some ability to develop appropriate methodology for a real data problem. While data analyst is probably just following a standard protocol, do the analysis one by one step. Like you memorize what's t-test and you just follow that procedure, right? But here I want you to think that, okay, there's some reason of doing this. It's not just a routine. We need to think why the routine exists. And if you have this mindset, it will help you trying to figure out a lot of the, I would say, seemingly mysterious things. Okay, so now let's revisit this topic. Why is this a t-statistic, right? T-statistic is defined to be a random variable that follows a t-distribution. Then we need to know what's the key component for t-distribution. So for t-statistic, so we actually require two things. So for the first one, it's a ratio. It's defined to be a ratio. And in the numerator, it must be a random variable that follows standard normal. That's what we need. And in the denominator, it must be some chi-square random variable. I'll just call it chi-square. With some degrees of freedom, I'll call df, divided by that degree of freedom. And furthermore, it requires the numerator and denominator to be independent of each other. So you need those three components to construct a t-statistic. And now we're going to show that our t-statistic defined in this way satisfy the three requirements. Oh, by that, I forgot a square root. It's the square root of this, yeah. Okay, so I think a lot of things can be verified for that thing. So like we can say the numerator I consider a standardized normal. That's not a problem. So we can see that, so basically we just want to fit in, right? Beta hat j, that's the numerator. We need to standardize it to be standard normal. And here we have this, it's sigma square hat times that jth diagonal of this, right? So we can easily verify that this is some chi-square here. We give you that already, chi-square n minus p. And we can verify this can be standardized standard normal here. So I'm going to leave this for you to verify. So this is easy, but the key thing is to show independence. So to show the independence, we need to show beta hat j is independent of sigma square hat. How do we show that? So this is something quite interesting to know. And if you think about this, it's essentially that because we know this term is just, we know it's just this, then it suffices to show. So we can just show that, okay, so this is sufficient. It becomes sufficient to show that beta j hat is independent of E. Okay, E is the residual vector. And furthermore, we can actually show beta hat is independent of E. So the coefficient estimate vector beta hat is independent of the residual vector. That's something quite surprising to us, right? Because we know beta hat is involved in the calculation of E. Since E is equal to Y minus X beta hat, then how can they be independent? I don't know if you still remember a similarly shocking result in the mathematical statistics is that we have the sample mean independent of sample variance if the sample are IID from Gaussian. So it's very similar to that. Gaussian gives us a lot of interesting results. So in the notes, we have a proof of this, but essentially the proof is going to use the property of multivariate Gaussian. That is, okay, so I'm going to just give you a thing. So basically here we have Y, right? Y is Gaussian. I'm going to put it here, n-dimensional Gaussian. Okay, and what we can say is that we can have AY independent of BY. So A is a matrix, B is a matrix if we have covariance AY, BY is 0. And here I need to make the notation a little bit clear. So probably if I can say this A, okay, I say this is n-dimensional. If I say A is m by n, let's say P is r by m. Okay, then this covariance matrix will be a m by r, 0 covariance matrix. That's what I mean. So if and only if, so or equivalent. This is the important property of Gaussian, multivariate Gaussian. So you can use 0 covariance to prove independence. But this doesn't hold in general. If they're not Gaussian, then we know 0 correlation or 0 covariance does not imply independence, but Gaussian is special. Okay, so in this case, to prove that beta hat and E are independent, we just need to use this property. We know beta hat is what? Is the X transpose X inverse X transpose Y, right? And E, we know it's the identity minus the hat matrix Y. So we're going to do that. So you see that here, to get a covariance matrix, I'm just going to show the covariance matrix of beta hat and E. And here, by definition, this will be a P by N covariance matrix. And here I have Y, right? So then it will just become, as I said, X. So this will actually, one more step, this will be equal to A times the covariance matrix of Y times B transpose. Okay, I'm going to use that here. So A is this, X transpose X inverse X transpose, and I have the variance of Y, or I should say variance, I should say variance here instead of covariance, and transpose itself, IM minus H, because of the symmetric property. And this variance is easy to deal with. It's sigma squared times diagonal. So I can put it forward, sigma squared, and I'm left with this thing times this thing. X transpose X inverse X transpose. Okay, and now I'm going to show that this is 0. Okay, so sigma squared, the first term stays. Minus, now I need H. If you still recall, H is defined as X times X transpose X inverse times X transpose. Okay, that's my H. And now you see I have cancellation. I can cancel this out. Then the two terms are equal. So I get 0. So this is just a very straightforward way to prove that beta hat and E, the residual vector, are independent under the normal assumption. So we satisfy the T assumption, T statistic assumption. And by the way, so coming back here, so the degrees of freedom in the denominator will just be the degree of freedom of my T distribution. So if those three components are satisfied, this is how we define t distribution. And just for your knowledge, chi-square, t, they're both arbitrarily, manually defined distributions. So as I said, people define them for convenience. So then they are defined to follow a distribution called t distribution with the degrees of freedom. Okay, so coming back here, we know our t distribution, this would follow t distribution with n minus p degrees of freedom. Okay, that's it. So we have t-test for each beta j. So if you want to know whether that beta j is 0 or not, you can do t-test. The next thing to talk about is a multivariate version of this test, and that's called the Wald test. Okay, so in the Wald test, it's trying to test whether a subvector of beta is 0, not just an entry, but a subvector. So to help you understand this, we're going to write beta as two subvectors. So let's just call this beta 1, beta 2. Okay, and let's assume that, okay, here it's P1 dimensional, and the remaining would be just, let's say, called P2 dimensional. And let's say P1 plus P2 equals P. So I divide my coefficient vector into two subvectors. So then accordingly, I can have my OLS written as beta 1 hat, beta 2 hat, right? And I can, accordingly, I can write my variance, the covariance matrix of beta hat, as a 2 by 2 block matrix. So by block matrix, I can write it as just the covariance matrix of beta 1. This is the covariance between beta 1 hat and beta 2 hat. Covariance of beta 2 hat, beta 1 hat, and finally, the covariance matrix of beta 2 hat itself. I can have this block matrix. Okay, with those, and of course, I can put a hat on each one, right? By putting hat, I'm going to use sigma square hat instead of sigma. And then do a hypothesis testing. So in the Wald test, the null hypothesis is whether this whole subvector beta 2 is a 0 vector with P2 dimensions. And of course, the alternative is it's not. Okay, and the Wald statistic. So this is, the name came from a pioneer statistician, Abraham Wald, and he has done a lot of important contributions. The Wald statistic is definitely one of them. So if you check his Wikipedia, you will actually find out a story of him in, I think, during the World War II, yeah. So that's about where, so like it's about how, which parts of a plane is most vulnerable. So yeah, I think that's a very interesting thing. You can think of it as a selection bias issue. I think, yeah, some of you know that. So basically, in short, the story is that, so people think the parts of the plane that has a lot of bullet hits were the most vulnerable, but he said no. Otherwise, you will not see the plane return to ourselves, right? So the unhurt parts are the most essential one. So that's the story of Abraham Wald. But unfortunately, he died at a very young age, I think only in the 40s, due to a plane crash. But still, during his very short career, he has left a lot of important contributions to us. So the Wald statistic, W, is defined as, so just to make sure that, you know, most statistics are scalars. So we summarize vectors into a scalar value to do the test. Otherwise, you can imagine if the test statistic is not a scalar, it will be not easy to compute what's a p-value, right? If you are under a multivariate distribution, how would you define a tail? That's not so obvious. So the Wald statistic is defined as beta 2 hat transpose times var hat beta 2 inverse. Okay, don't forget this is an inverse times beta 2 hat. So you see this is a 1 by P2, P2 by P2, P2 by 1. So that's why it gave us a scalar. And you see this is the multivariate version of the T statistic, because if P2 is 1, okay, if this is just one dimensional, then the W is just the square of a T statistic. Okay, so still under the normality assumption, so we can show that, oh, by the way, sorry, this is something I forgot to say. Under here, when I say this follows T distribution, I must specify that this is under the null hypothesis. Under the null hypothesis beta j is 0, this is T statistic, T distribution, because you see, only when beta j is 0, I can have a beta hat j with mean 0. Otherwise, the mean will be beta j, not 0. Okay, so coming down here, under the null hypothesis, that is the beta 2 is a 0 vector, we can show that the W, the Wald statistic, divided by P2 dimension, this will follow an F distribution. F distribution with, it has 2 degrees of freedom. The first one is what we call the numerator degrees of freedom, it's P2. And the denominator is what we call the denominator degrees of freedom. Sorry, the other second is the denominator degrees of freedom is n minus p. Why is that? So this is also related to how we define an F distribution. So in this definition, it's defined as a ratio where the numerator and the denominator are both chi-square random variables. Numerator must be chi-square P2 divided by P2, and the denominator must be chi-square n minus p divided by n minus p. That's how we define an F distribution. This is also part of the contents in the undergraduate mathematical statistics. So coming back here, you can see that in order to show that, we basically just need to show, okay, how can we write this in terms as a ratio of the F statistic? And, or probably I think we can, so basically this is something we want to put in this form so they satisfy definition of the F statistic. But roughly speaking, I want to give you some intuition is that you can consider this as beta 2 square, beta 2 hat times itself. So you would have the square formed by beta 2 hat transpose beta 2 hat. And you will consider this middle part in the row as a denominator. So in this part, what is unknown here, or what is the plug estimator is the sigma square hat, okay? That by that error term, sorry, that variance estimator. And we already know that that term itself has n minus p degrees of freedom. And here in this numerator part, we know beta 2 hat has P2 parameters. So it has P2 degrees of freedom. So that can help you understand why we have P2 as the first degrees of freedom and n minus p as the second degrees of freedom. Okay, and one more thing is that, and also this division by P2 is because of this thing. We need to divide by degrees of freedom. It's not there yet. While in here, because the definition of sigma square hat involves a division of n by p. So we're already satisfied this. So again, similar to the T distribution, we know that the T n minus p is convergent to standard normal as n goes to infinity. We can also have this asymptotic result. So when n goes to infinity, we will actually have W follows chi-square distribution with P2 degrees of freedom. So there's also a similar relationship between the F distribution and the chi-square distribution. In other words, P2 times F P2 n minus P is convergent to chi-square P2 as n goes to infinity. Let me put it here. Yep. So you can think of F distribution as a finite sample, small n adjustment for chi-square, while T distribution is a small sample adjustment for standard normal distribution. Okay, so that's the Wald test. It allows you to test whether a subvector of beta is 0. And furthermore, another thing we often use in practice is what we call the likelihood ratio test. So you can think of likelihood ratio test as a more general test. It's not specific to linear model. While the Wald test we just gave you, that one is for linear model. Okay, so you can think of Wald test as kind of a specialization of likelihood ratio test in linear model. Interestingly, even though their test statistics are not exactly the same, and similar, not exactly the same, but the distribution can both be chi-square. So let's think of the test statistic here. So likelihood ratio test statistic, we call it, so let me still specify it, okay? So H0 is beta 2 is 0, okay? This can be considered as a smaller model because we are basically saying that the predictors corresponding to those coefficients are not needed, right? They do not have effect, so we can remove them. This is corresponding to a smaller model. Versus when we say beta 2 is not equal to 0, this can be considered as a full model, right? This is our starting point. And then the chi-square, sorry, not chi-square, then the likelihood ratio statistic, we use this capitalized lambda. So this is a Greek letter lambda in capital. And so this is defined as the maximum likelihood of beta when the null hypothesis is valid. Under the null hypothesis, we find the maximizer of the likelihood and we return the maximum likelihood. So this is a constraint optimization. We're doing maximization with this constraint. While the denominator is for the full model, so we don't have the constraint, we still take the maximum likelihood. So of course, we know it's often easier to deal with log likelihood, right? So we have the log lambda, then that's just max minus, okay? And now this is the general form. General form for likelihood ratio test. It can be used for comparing two models, one nested under the other. So we can say the smaller model is nested under the full model. Then specific to our linear model, if you recall the log likelihood form, I'm going to show you that again. So it's here, the log likelihood of linear model. So you see that beta is only involved in the second term. So when we have two likelihoods to do the subtraction, this term can go away. We are only left with this, okay? So, and this is actually what? If we plug in beta hat for beta, right? Since we're doing the maximization, after maximization we have beta hat. This is just the summation of residual square or our RSS. And then the sigma square stay here. So now we are just looking at beta by assuming sigma square to be known. So this will give me negative 2 sigma square. And it's RSS H0 minus RSS, the full model. So the constraint RSS minus the full RSS. So this is from our linear model with the normality assumption. That's the result. So if we multiply -2 to the left-hand side, we will get -2 log lambda equals sigma squared RSSH0 minus RSS. And you can see that this is a positive term because under H0, we have fewer predictors in the model, right? We have a constraint. So you can imagine that for sure, the RSS under the constraint will be no smaller than the RSS without the constraint. Because without the constraint, we can always fit the data better and make the residual smaller. So this will be a non-negative term. But we cannot use it as a test statistic yet because sigma squared is unknown, right? How can we deal with that? We still use our estimator. So here we do plug in again to construct our test statistic. So I'm just going to put this hat here, and this is going to be, okay, for this one, I can say it's RSS divided by n minus p. This is our sigma squared hat. So now I have a question for you to think about. So for this denominator, why do I use the RSS obtained from the full model instead of the reduced model, the smaller model? What's the reason behind that? This is a question a lot of students will wonder when they first see this formula. So I think to me, the best justification is that when we do this whole test, our starting point or our underlying assumption is that we think the full model is the true model. So given that true model, we are wondering whether a portion of the coefficients are zero. But no matter whether it's zero or not, it doesn't affect our belief that the full model is the true model, not a smaller model. So that's why when we calculate this sigma squared hat to estimate sigma squared, we must use the model we believe in, and that's the full model. So that's why here the estimation of this parameter is not about beta, but about sigma squared. We are going to use the full model. So I think that's the best justification to me. And in statistics, many people say, okay, the sigma squared is not the parameter of our interest, right? Our parameter of interest is beta. So sigma squared in that sense is something we can call it an ancillary parameter. It's actually not directly related to the interest, but it's something out there, and it's unknown. We must estimate it. So that's why here, when we estimate the sigma squared, we use the model we think we start from, but not the beta we're interested in. So it's not really related to whether beta 2 is 0 or not, because no matter what, we are still trying to fit the full model as the starting point. So that's why we're doing the RSS instead of the RSS H0. We don't want to get the null hypothesis into the estimation of this ancillary parameter. Okay, so for the likelihood ratio statistic, there is asymptotic theory for that. So asymptotically, we're going to just do that. As n goes to infinity, we would have this statistic, -2, will follow under the null hypothesis chi-square distribution. And the degrees of freedom is the different number of parameters between smaller model and full model. Oh, sorry. Yeah, I think that's, yeah, that's right. And the difference is P2, because here you specify the P2 parameters to 0, while here you do not. So it's the chi-square P2. So you see, this is similar to the Wald test in terms of the limiting distribution, but the test statistic is different. It's not the W, but it's the log likelihood ratio. They're slightly different. Okay, so we'll stop here, and starting next time, we'll talk about the ANOVA. But just to give you maybe a take-home question for you to wonder. So if I'm really interested whether the P2 parameters are 0 in beta 2, can I just do P2 t-tests for each element and combine them? Or would it be better to do the likelihood ratio test or Wald test? Okay, I'm leaving this as a question for you to wonder, and I'll ask for your thoughts next time. So see you on next Tuesday.